Welcome to Get EDUCARE. In this video, the losses of transformer will be explained. Also, the copper loss will be discussed. Generally, there are four types of losses in transformer. Number one is copper loss. The primary winding has resistance and the secondary winding has resistance. Whenever the current passes through the winding, then there is a I square R loss in the transformer winding. This I square R loss is called the copper loss. Now, if the load resistance is RL and depending upon the load resistance, the load current will be the IL. Therefore, the copper loss depends upon the load current. Depends on load current IL. Since the load current is variable, it depends upon the type of load. Therefore, copper loss is a variable loss. Number 2 is the Aeron loss or core loss. The losses in the transformer core, this is the core of the transformer. Here the losses in the transformer core is called the core loss or Aeron loss. The Aeron loss depends upon the supply voltage and frequency. Depends on supply voltage and frequency. Since the voltage and frequency is constant, therefore it is a constant loss or fixed loss. Constant loss or fixed loss. Number 3 is the stray load loss. The losses in the transformer body structure is called the stray load loss. Number 4, dielectric loss. The losses in the insulating material is called the dielectric loss. Mainly, the copper loss and iron loss has the major contribution of losses. Therefore, it is called major losses. And stray load loss and dielectric loss has a minor effect on the losses, therefore it is called the minor loss. Now, the iron loss or core loss can be classified into two categories. Number 1, hysteresis loss. And next one is eddy current loss. What is hysteresis loss? What is eddy current loss? Will be explained in the next video very clearly. This is the equivalence circuit of transformer. Here the shunt branch parameter has been neglected. Let the primary winding resistance is R1, reactance is X1, secondary winding resistance is R2 and reactance is X2. Let the secondary current or load current is I2 and the primary current is I1. Therefore, total copper loss is equal to the I square R loss in the primary winding. That means I1 square into R1 plus secondary winding copper loss, that means I square R loss, that is equal to I2 square into R2. Now, the secondary winding resistance R2 can be transferred to the primary side and it becomes R2 dash. Similarly, the x2 can be transferred to the primary side and it becomes x2 dash. Now, this is the R1, this is the R2 dash, this is the x1 and this is the reactance x1 dash. Let the primary winding has n1 number of turns and secondary winding has n2 number of turns. Now, since R2 is transferred to the primary side, therefore R2 dash will be the n1 by n2 square into R2. Similarly, x2 dash will be given by n1 by n2 square into x2. Now, let the primary current is I1 and these two resistance R1 plus R2 dash becomes R01. That means total resistance with respect to primary is equal to R1 plus R2 dash, that becomes R of 01. Therefore, total copper loss with respect to primary is given by I1 square into R1 plus I1 square into R2 dash, that is given by I1 square into R1 plus of R2 dash, that is equal to I1 square into R01. Similarly, the primary winding resistance R1 can be transferred to the secondary side and it becomes R1 dash and X1 becomes X1 dash. From this figure, here this is the R1 dash, this is the R2, this is the X1 dash, this is the X2. These two resistance R1 dash plus R2 is given by R02. Here this is the n1 number of turns, this is the n2 number of turns. Here R1 dash is given by n2 by n1. Since R1 dash is transferred to the secondary side, therefore n2 comes first. Therefore n2 by of n1 square into R1. Similarly, x1 dash equal to the n2 by n1 square into x1. Therefore, total resistance with respect to secondary is given by R1 dash plus of R2, that is equal to R of 02. The total copper loss is given by I2 square. Here let the secondary current is I2 square into R1 dash plus I2 square into R2, that is given by I2 square into R of 0 2. Therefore, we can say the total copper loss of transformer is equal to the I1 square into R1 plus I2 square into R2, that is equal to I1 square into R01, that is equal to I2 square into R02. Now we'll make a chart of load current and copper loss. Let the load current is the full load current. Load current is I of full load current. Then the copper loss, full load copper loss at full load is the I square R loss, means I of FL R square into R of 0 1. Here I1 equal to the full load current I of FL. Now when the load current is half of full load, half of I of FL, then copper loss at half of full load is given by half of I of FL R square into R0 1, that is given by 1 by 2 R square into I of FL R square into R0 1, that is equal to 1 by 2 square, that is equal to full load copper loss, full load copper loss. Again, when the load current is X of full load, then copper loss at X of full load will be given by X into I of full load R square into R0 1. Then I can write down from here, जो X square into I of FL R square into R0 1, that is equal to X square into copper loss at full load. Now, when the current is full load current, that is I of FL, then the full load copper loss is I of FL full load square into R0 1. When the current is half of full load, then the copper loss will be the half square into full load copper loss. When the current is X of full load, then copper loss will be the X square into full load copper loss. Therefore, we can conclude that the copper loss at X of full load is equal to X square into full load copper loss. This is one of the important relation we should remember always, very important relation. That means if the copper loss of any load current is given, then we can easily find out the full load copper loss using this formula. Now again, the copper loss at full load is given by I1 square into R01, where I1 is the full load current. Now per unit copper loss is given by this total copper loss divided by rating of the transformer I1 into E1 rated. Similarly, per unit copper loss at half of full load is given by I1 divided by 2 the square, current is half, into R01 divided by I1 E1 rated. That is equal to half square into per unit copper loss at full load. Therefore, we can say the copper loss, per unit copper loss at X of full load, that means per unit copper loss at X of full load is given by X square into per unit full load copper loss. This is again the important relation, whether it is the absolute value or per unit value. Previously we have derived the absolute value, that copper loss at X of full load is equal to X square into full load copper loss. Again, per unit copper loss at X of full load will be given by equal to X square into per unit full load copper loss. Now, the copper loss depends upon two factors. Copper loss is the I square R loss. That it depends upon the load current and the resistance of the winding. Is the load current and R is the resistance of winding. Okay. Now, the load current is not the fixed. It depends upon the type of load. Therefore, copper loss is also not fixed. The copper loss is a variable parameter. And the resistance should be as minimum as possible, so that copper loss becomes minimum. Therefore, the winding of transformer is made of good conducting material. Let us practice a numerical. If short circuit test is performed on 90% of rated current, the wattmeter reading is 81 watt, then what is the full load copper loss? Here the given is copper loss at 0.9 of full load current I of FL is 81 watt. has been given. Now we have to find out what is the full load copper loss. Full load copper loss equal to how much? We have to find out it. Now copper loss at x of full load is given by x square into full load copper loss. Therefore, copper loss at 0.9 of full load is given by 0.9 square into full load copper loss. Okay. We know the copper loss at x of full load equal to x square into full load copper loss. Here x equal to 90%, that is equal to 0.9. Here x equal to 90%, that is equal to 0.9. Here that is given equal to 81 watt. You can do 81 equal to 0.9 square into full load copper loss. Therefore, the full load copper loss is given by full load copper loss is given by 81 divided by 0.9 square, that is equal to 100 watt. That is the answer. Thank you for your continuous support to get EDUCARE. A lot of positive response has been given to my channel. Okay. That gives me motivations. Thank you once again, all of you. Please subscribe my channel and share it to all of friends for your further notifications and new videos.